Well, welcome everybody. It's my great pleasure to introduce tonight's speaker, Professor Matthew Bales from Swinburne University in Melbourne, Australia. Matthew was born in Alice Springs. I learned that just today, in Alice Springs, Australia, and did his PhD at the Australian National University and got his degree, his PhD in 1989. With a thesis titled The Origin of Pulsar Velocity. So he was fascinated by neutron stars and radio pulsars. And his PhD thesis was the pretty famous Richard Manchester from Australia, who also happens to have been one of my PhD thesis advisors. And that makes Matthew and me sort of research siblings. Except Matthew's a few years older than me. And I was a graduate student when he was a postdoc. And he was I'll just say, tremendous mentor to me and good friend. And I learned so much and continue to learn a ton from him today. After getting his PhD, he first moved to the Goddard Space Flight Center in the United States, and then after to the University of Manchester in England, before returning home to Australia with a prestigious Queen Elizabeth II fellowship. After that, he was awarded an Australian Research Council Laureate Fellowship in 2015 and continued to do groundbreaking work in the field of radio pulsars. Matthew's written many papers, and some I've even been a co-author on, I think, on binary neutron star evolution, how two neutron stars orbit each other, on testing general relativity, Einstein's theory of general relativity using binary pulsars. He's a master at searching for pulsars. He's developed tons of fascinating instrumentation. So he not only does he analyze data, he also does instrumentation for radio telescopes. And he was elected as a fellow of the Australian Academy of Sciences in 2022. And in 2023, he won the Shaw Prize in Astronomy, which some people claim is like a Nobel Prize in Asia, the Asian Nobel Prize, for his co-discovery of the phenomenon called fast radio bursts with his former student, Duncan Lorimer, and Maura McLaughlin. And I got to enjoy a fun party in Hong Kong this fall when he was awarded that prize. Today, he's the director of AusGrav, which is Australian Research Council Center for Excellence in Gravitational Wave Astronomy. And as his friend, I feel I have to tell you some funny anecdote. And I just want to tell you one of the most vivid memories I have of Matthew from years ago when we were at a conference. This is many, many years ago when dinosaurs roamed the earth. And I was a student and he was a postdoc. And at that time, when you made a presentation, you did it using transparencies, these acetate sheets that you put on an overhead projector and you lit it up and it projected it. And my students who are in the audience remember, I told them the story just a few days ago. But I remember we all had our acetates, we went up, and then Matthew's turn came. And he dimmed the lights in the room. There was this dramatic pause. And suddenly he turned on a computer and he displayed this software called PowerPoint. And we could not believe what we were seeing. And words were sliding across in all sorts of fonts and sizes, and slides were changing by turning and rotating and whizzing by. And I don't remember at all what the talk was about. And in fact, 5 minutes later, nobody in the room could tell you what the talk was about, but we all saw this amazing future of how science communication would be done. And Matthew has always been at the forefront of science communication, astrophysics, data visualization. So it's my great pleasure to have you get to see what he's doing these days. So Matthew.
Thanks very much. So for my talk, I'm going to be using something called AusGrav's virtual universe.
And instead of using PowerPoint, so I've moved on, I'm going to be using something called OzView, which stands for Ozgrav's Virtual Universe. And we're going to start this talk at the Earth and how observations and theory have guided our understanding of how the universe works. And the title of the talk is A Virtual Tour of Einstein's Universe, but I thought it might be good to put into context where we live. And indeed, right on cue, the mighty Australian continent is coming online. And I think I can, what's happened to my keyboard? Oh, I just need to click. Right, so I think this is going to work. Oh, there we go. So I'm from Australia, as Vicky said, and not only did I win the QE2 fellowship to come back to Australia after a time in a frozen England. Well, it was more drizzly and rainy. But anyway, I went back to Sydney, which is like a paradise on earth by at least some conditions, and it was on a QE2 fellowship, which was a fellowship. And by coincidence, I was in a very small town when I was born in Alice Springs, which is right in the center of Australia. So let's visit. And Alice Springs is one of those dots in the middle. I think the other one is a US base or something. And it just so happened that even though there's only 5,000 people in Alice Springs, where I was born, Queen Elizabeth II was actually visiting. So I was fated to win the QE2 fellowship all those years later. But we are currently in Canada, which is a great distance from Australia, hearing talk about gravity. And we're going to fly around my virtual universe and learn about the stars and space. So for many years, people have been observing the heavens, and you'll see these magnificent sky maps. This is actually a texture map from the Gaia satellite, and there's dust, and people have been observing the heavens, but we only really started to understand it when we made detailed observations and connected it with mathematics. And so for many years, the ancients knew that the stars were somehow different than the planets. So if I was to look at Mars from Earth, which I can do, Mars is that little blob there, right here. And by the power vested in me, I can actually speed time up and slow it down, which is kind of handy. So let's watch how Mars drifts through the night sky. And you can see it tracks from right to left. Sorry about the glitchy thing. I blame Zoom. And so it traveled through the skies, and the ancient people knew that the planets were somehow different than the stars that were always in the same place. And if we speed up time a great deal, and this is how many days per second are going by, you'll see that Mars goes from right to left, and it's traveling through the constellations and giving people who believe in fortunes strange things to say. But then we eventually get to a certain phase of the Earth's orbit, actually, where Mars stops going from right to left and actually will turn around and go backwards. And the Greeks knew about this and used to call it an epicycle. But it's going to happen. It's slowing down. So you see those stars, and then we go backwards for a little while. This is why the Earth is kind of in the overtaking lane on the inside of the Earth. And then it goes forwards again. And in fact, all of the planets do this. And so we can have a look at, say, Jupiter. Oops, we're flying to Jupiter. Sorry, let's go back to Earth. And we'll look at Jupiter. And there's its moons. I'm going to take them away because it's a bit distracting. But similarly, if we speed up time again, you'll see Jupiter's going backwards. The sun goes by. Oh, I think we're actually going a bit too fast. So all of the planets do this thing called retrograding, where they travel in one direction, but then go backwards. And it was Copernicus that first came up with the idea that maybe the Earth isn't at the center of the universe, maybe the sun is, and the planets go around the sun. And he had the genius to work all that out without very precise measurements of the positions of the stars and so on. And we can see how that works by putting the Earth, the sun at the center of the solar system. Zooming out a bit. We'll keep going until, well, there's Mercury, there's the planets, and if we leave their trails on and speed up time, we'll see that from a sun's perspective, the planets go around in nice, almost circular orbits. They're actually slightly eccentric, and we'll learn a bit more about that later on. But the closer you are to the sun, the faster you go around. And Copernicus had his sun-centered universe model. If we were to put the Earth at the center of our universe and zoom out from there, sorry about the headache, you'll see that everything has to go in very weird trajectories. And it's a very sort of crazy universe where things are both going around the sun, but also kind of going around the Earth. And so Copernicus had put forward this idea that maybe the sun was at the center of the universe, and or at the center of the solar system, sorry. And we all know that's very sensible. But when you live on the Earth, it's easy to think you're the center of the universe. And if you live in America, that's also true. The first time I ever met my Canadian cousins, we weren't getting on very well. And then I started talking about guns and healthcare and America and stuff. And we were like blood brothers. It's beautiful. Anyway, so Galileo was the first person to grab a telescope and point it at the sky that we know of. And he pointed it at Jupiter. So we can do that ourselves. If we slow down time a bit, so I don't want to make you sick. What he noticed when he looked at Jupiter was amazing, that it actually had its own moons. And so you can see them labeled there. In the background, we can fly out a little bit and see what he saw. And that there was let's get rid of these pesky other planets. He could see that there were 4 moons, and every night they were in a different position on the sky. And they seemed to occupy a straight line. That's because they're all what we call coplanar. And he thought, well, if Jupiter has moons and the Earth has a moon, well, maybe we're not very special. And so he also believed that maybe the Earth wasn't the center of the solar system, and he was put under house arrest because of this and was somewhat persecuted. Luckily, nobody's tried to do that to me for my fast radio burst and pulsar research as yet. So this use of a telescope was actually instrumental in learning where we were in the universe. And it was later shown by Newton and others that there were physical equations that could describe the motion of the stars and planets across, or the planets around the solar system. So let's just do a little tour of the solar system. So this is our sun. It's called a yellow G2 star. It weighs 1 solar mass, which is remarkable. And it takes light about 500 seconds to travel from the sun to the Earth. It's orbited by a series of now 8 major planets. The first one is Mercury, and Mercury looks a lot like a moon, and we can like spin around that. and see that just like our moon has craters and impacts, it has very little atmosphere. It's only about 5% of the mass of the Earth. So it doesn't have enough gravity to keep any atmosphere. And it's incredibly hot on the sunward facing side and incredibly cold on the rear. And it actually rotates every 66 days, but it goes around the sun about every 100 days. And so a day on Mercury is extremely long because it's almost rotating around as fast as it is going around the sun. And this is probably due to some sort of tidal locking. And we can fly off to Venus now, which is the most Earth-like planet in terms of its mass, but it's actually much, much hotter. And this is because it has enough carbon dioxide to keep in the radiation. And it's something like 400 degrees and it rains sulfuric acid. And it's just a generally nasty place to try and live. It's kind of boring. It doesn't have any moons, but the year is only about 2/3 of our year. So we've already been to the Earth. We can go to our moon and see how much it looks like Mercury. And we can even do fun things where we could look at the Earth whilst orbiting the moon, which is kind of fun. So let's do that. And you can see how big the Earth is from the moon. It's rather kind of tiny. And there was a famous photograph taken by one of the early astronauts who, when orbiting the moon, took a shot of the Earth doing what he called Earthrise. And if we're really lucky, we might be able to do that too. Get your cameras out. So this is the moon is about to obscure the Earth. And then when we go past, we will see the Earth hopefully rising above the moon, which is kind of fun. So it's about now. I'll put the cursor here. There it is. There's the Earth. Don't know if you can see it or not. So anyway, one of my favorite planets is Mars. So let's fly there. Hope we're going to fly there. So let's slow it down a bit. Mars has these remarkable volcanoes, which are the biggest in the solar system. This one here that we're looking at is Olympus Mons. It's actually 27 kilometers above sort of sea level, if you want. And then it has these other little baby volcanoes. And if you could stand on Mars, you can't actually see the surface of Olympus Mons because it curves so much. Mars is only about 1/3 of the radius of the Earth. So you could actually jump about 3 times higher on Mars than you could on Earth. It has 2 little tiny moons. The first one, I think, is called Phobos. And we might have a look at Mars from, remember how to do it, whilst orbiting Phobos. Phobos is only about 10 kilometers in diameter. It's a very tiny moon. And it actually goes around Mars every 4 hours. But Mars takes 24 hours to rotate. A Martian day is about the same as the Earth day. And in fact, it goes around so quickly that instead of rising in the east and setting in the west, it does the opposite. So it's also not big enough to be spherical. So its gravity isn't strong enough to get over the interatomic forces. So you can see Phobos is this sort of potato shape. And it has a companion moon, which we can also fly to, called Deimos, which takes considerably longer to go around. And it's thought that Phobos will eventually be tidally destroyed by its moon. So let's go to Jupiter now. Jupiter has something like 67 moons, I think, at last count. It's an incredibly large number. There's only 4 of them are worth thinking about. So there's Io, which is the kind of volcanic one. Io is so close to Jupiter and Jupiter is so massive that it actually gets tidally squished. And so the whole thing is like a volcano. And in fact, when the Voyager probe, I think it was, flew past, you could actually see an erupting volcano on the horizon. My program can't do that yet, but stay tuned. There's 4 other moons, and they have these remarkable structures and streaks, which are beautiful to look at. Saturn is one of my favorite planets. It has these beautiful rings around it. The rings are hard to see if you do graphics properly and you're on the non-sunny side. So let's tilt it a bit. Spin around. So Saturn has this beautiful ring system. These are basically like pulverized moons that form this planar disk. And there's even little baby moons inside the disk, which help create those gaps, one of which is called Cassini's division. Let's just go to Titan briefly, which is one of the major moons of Saturn. And we can have a look at what Saturn looks like from the moon. So it's a fair way out. But again, we can get some nice views of what it would be like orbiting the moon and looking at Saturn. The last 2 moons now, the last 2 planets in our solar system, Uranus and Neptune, they're rather featureless, and I don't have any moons of them, and I'm not even sure if there are any. These are what's called the gas giants. So they have a density only about 1/3 of the Earth and reasonably boring weather systems and so on. So let's now abandon the solar system and learn a little bit more about Einstein's universe, now that we have some knowledge of our own. All right, so we're going to be learning about exotic things like neutron stars and black holes. As Vicky said, I'm from Swinburne in Melbourne, Australia, but my true love is actually pulsars. And fast radio bursts have been good for a laugh, but the true faith return. And so we'll be learning about neutron stars. Neutron stars are these amazing things that made me want to be an astrophysicist in the first place. A teaspoon of a neutron star weighs more than all of humanity. So the density is remarkable. They're only about 20 kilometers in diameter, but the gravity on these systems is so incredibly strong that if you took a brick from this distance and threw it on there, it would give off about the same amount of energy as the Hiroshima atomic bomb. They have these remarkable magnetic fields and beams of emission that enable us to see them. So let's learn a bit about these systems and how we can use them to explore gravity in more detail. So Johannes Kepler teamed up with Tycho Brahe, who was the greatest observational astronomer of his generation, and also had a golden nose. I think that it lost in a duel or something. And Brahe wasn't much of a mathematician, but he had an apparatus that he used to measure the positions of the planets very accurately. And Kepler took that data after some fights. They had an adversarial relationship. I think after Tycho had died, Kepler had unfettered access to the data. Vicky and I don't fool our competitors, but so maybe if they had a gold nose, more tempted. And Kepler worked out that the planets actually travel in elliptical orbits. This is like a circle seen edge on. They swept out equal area in equal time, and that there was a numerical relationship describing how long they took to get around or to complete one rotation and the distance from the system you're orbiting. So this thing here is an ellipse, and you can draw an ellipse by getting 2 pins and sticking them in the ground and attaching a bit of string, and then keeping the string taut and drawing around a shape, and you end up with what's called an ellipse. And where the pins are, that is what's called the focus. And so if we put the sun at one focus, we can actually describe the motion of the planets very accurately. And the amount of area that's swept out in a given time interval is the same, no matter whether you're at what's called perihelion or aphelion. And so in my little diagram there, oops, I put on trails, this planet, which is actually Mars, you might recognize it. It doesn't go in an orbit anything like this, but it's much more fun this way. So that is an elliptical orbit that you're seeing there. Sorry about the flashing. So there's an elliptical shape, and it goes faster when it's near the sun and slower when it's further away. We can see that a bit more clearly in the next slide, or a bit bigger, shall we say, where it's tracing out its elliptical shape. And if we return to our solar system, we look very carefully, we'll be able to convince ourselves that actually the planets do really go in elliptical orbits. So if I put on the trails and find my long lost planets and speed up time, we're going to need a few hours per second to be able to notice their trajectories. You can see Mercury is the closest planet, and we can see the path it's tracing out. We've got Venus is next, and then the Earth. And if we get right above this, you can see that Mercury is indeed tracing out an elliptical orbit, and that it's closer to the sun at this time of year than it is over here. I don't know if you're going to be able to see it going faster when it's over here, but pretend you can see that, and we'll all be good. And so the amount of area it's tracing out per unit time depends on that distance to the sun. And then the amount of time it takes the different planets to go around depends on how far away they are from the sun. So you can see that the Earth is more than double the distance of Mercury, and Mercury is beating us in terms of lap times. And so Kepler had the patience and also the mathematical ability to be able to work out these amazing relationships between how far away all the stars were from the sun and how fast they went. And if we zoom out far enough, these are what's called the inner planets. These are the so-called rocky planets. There's an asteroid belt, which I don't have in here, but trust me, it's between Jupiter and Mars. And then we have these other planets, and you can just keep zooming out. Now, unfortunately, what happens in these computer simulations of the solar system is that if you make everything the right size, apart from the sun, everything looks like a dot. So the planets aren't actually that big, and Saturn's rings don't extend that far, but it's just so you can help visualize it. And you can see those inner planets are traveling around very quickly. Poor old Neptune is going to take over 100 years to complete its orbit. So Newton came along over 100 years after Kepler. She was 100. 1666 was the Great Fire of London, when he developed differential integral calculus whilst locked down. It was like COVID at the time, the Great Plague of London. And he also developed his theory of gravity while he was in exile at his property. I think he was only just over 20 years of age at the time. And he had thought about how the laws of motion work for objects on Earth, but he also came up with what is called the universal law of gravitation. And he wondered why, if everything was attracted to other bodies in the solar system, why they didn't crash. And so he came up with something called Newton's canon, which explained why the moon doesn't collide with the Earth if they're experiencing a force of gravity. So in Newton's laws of motion, the force you feel depends on your mass and your acceleration. So if you're being accelerated, if I jump up in the air and land, I'm being pulled by the force of gravity, and the rate at which my velocity changes depends on certain fundamental constants, like Newton's gravitational constant, the mass of myself, the mass of the Earth, and the distance from the center of the Earth. And so Newton came up with this thought experiment where he took the moon and he said, what if I just dropped it? What would happen? And so I have the ability to do that. So watch the moon. fire. It's just going to fall onto the Earth and disappear. And then doesn't really fly out the bottom, but the computer engine has a slight. And then thought, what if I fire the cannon a bit faster? And so the moon will be flung out. What's going to happen is, under his universal law of gravitation, it's sort of like a law of love, the moon and the Earth are going to attract each other. They're going to want to fall together, but the momentum of the Earth is, or the moon is going to stop it falling into the Earth for a little while. And if you get a moon and you fire it out, it still plunges into the Earth. If we do it again with a slightly bigger kick, it falls and it almost makes it, but then still crashes into the ocean somewhere near the equator. And then if we were to fire the cannon, if we got a bit crazy and put too much gunpowder in it, we could actually fire the moon out and actually have it escape the gravity of Earth. But there's a special speed, which is about 7 kilometers per second, at which the moon, if it was this far above the Earth, apart from creating really crazy tides, would actually go around in a circular orbit. And so Newton used his laws of mathematics to show that the reason the moon didn't fall onto the Earth is because it has its own momentum. It wants to go in a straight line, but the force of gravity is making it fall at exactly the same rate that the Earth is curving. But the moon, of course, is actually much further than it's about 400,000 kilometers away, and the Earth's radius is only about 6,380 kilometers. So this is a bit diagrammatic. But you do get these nice demonstrations of how the force of gravity and Newton's first law, which is things don't actually change their velocity unless acted on by a force, can explain the circular orbits of systems. So Newton was very good at not only deducing or explaining why the moon doesn't fall onto the Earth, but he showed that Kepler's laws were just a consequence of his 3 laws of motion and the universal law of gravitation. So making it go a little bit faster, you can see that you get this nice circular orbit. And this is what satellites do in order to stop them falling down. There's not much atmosphere, so satellites will orbit for almost ever, creating space junk. Now, what's quite interesting is that in the 1960s, when I was a little boy, there was something called the Colgate ring of confidence. And if you were a nervous woman, you could use Colgate toothbrush. And then, according to the advertisements, when your shooting instructor was teaching you how to fire your gun in an American commercial, you would actually have this thing that would go ding, and it would be a ring. And so, remarkably, the Earth has its own Colgate ring of confidence, which looks remarkably like this woman's ring of confidence. And back in the 60s, this is all that women had to worry about, was their breath fresh, and would their shooting instructor be attracted to them because they had the Colgate ring of confidence. And I actually have brought with me a tube of Colgate. It's in here somewhere. I don't know, I left it at home. Oh no. Yeah, I'm going to look for it later. The talk better keeps going. But I actually had some Colgate if anybody's having a few confidence issues. All right, so the theory of gravity didn't really advance very long after Newton explained all of the motions of the planets and so on. But Einstein came along and he loved doing these remarkable thought experiments. He wanted to think about how the universe worked. And he realized that maybe if you were in an elevator that was soundproofed, you wouldn't be able to tell the difference between experiencing the force of gravity and if that accelerator was being accelerated in outer space, maybe the forces you felt were entirely equivalent. And so this is what's called the equivalence principle. And he thought maybe if you did an experiment, is there any experiment you could do inside this elevator that would enable you to tell the difference between acceleration due to gravity and acceleration due to, well, acceleration? And the idea was no. And this would have lots of consequences because he thought maybe if you're free falling in gravity, a bit like the moon was, you wouldn't be able to tell if that was happening to you or whether you were in outer space and not accelerating at all. And so if you could imagine shining a torch inside your elevator, if you had two mirrors and the light was bouncing between the mirrors, if you were free falling in gravity, then light must bend under gravity as well. And so this had a number of consequences for the universe. It's kind of a little bit hard to test. But one of the consequences was that, well, light should bend when it goes past a heavy body. That time should go slower when experiencing strong gravity than when in distant outer space. So if you have a clock and it was ticking on Earth and you took that same clock into outer space, it would actually tick more quickly. And in fact, you need to make that correction, otherwise GPS doesn't work. So we actually know that this works very well. That space would be compressed near bodies, and that there'd be a limit to how compressed you could make an object, which is given by this formula here, the radius 2gm upon c squared. What does that mean? It means if you took the Earth, you'd have to constrict it to a radius of 1 centimeter to turn it into what's called a black hole. So at this magical radius, light couldn't even escape an object. But it's very hard to compress the Earth to something only 2 centimeters across. The other thing he predicted was that any two bodies going past each other should emit something called a gravitational wave. This is a bit like an analog of a light wave when two electrical objects go past each other. And he worked out the amplitude of this gravitational wave. And if you do that, you can actually do this computation. And what you find is that the amplitude of a gravitational wave being driven by the sun or being generated by the Earth and Moon would cause space and time to compress by 1 part in 10 to the 15. What does that mean? That means that if you had a ruler which was 1,000,000 kilometers long, if a gravitational wave went through it generated by the Earth and Moon, it would shrink by about the radius of a proton. And in order to be able to measure that, you'd have to be able to have a 1,000,000 kilometer ruler and go, oh, it's changed by the radius of a proton. That's extremely difficult. And not only that, the apparatus would have to be 150 times the distance to Neptune. So one of his predictions was that the orbit of Mercury, or the elliptical shape of the orbit of Mercury, should have what's called a perihelion advance of 43 arcseconds a century. So that's about 1/100th of a degree. So the distance of closest approach for Mercury should change by, if we zoom out again, put on our trails. So Mercury's orbit was elliptical. We saw that before. So this point of closest approach here should actually move forward by 43 arcseconds every 100 years. And somehow people had already measured that back in Einstein's time. And so his general theory of relativity was the first to actually explain it. I think that means in 100 years, Mercury moves by, or the distance of closest approach goes by about the radius of Mercury. So it's kind of astonishing to me they can even do that. But 43 seconds of arc a century is enough not to be able to convince too many people that other strange things like tides on the sun or the other planets aren't actually causing it. So it had some degree of acceptance, but maybe there was a little bit of skepticism. There was also a prediction that if there was a total solar eclipse, then the apparent position of the stars should change as the light bent around. And Eddington did an expedition to map the positions of stars during a total eclipse, but he kind of knew the answer. And there's some degree of skepticism about whether he knew how many arc seconds the stars should have to move. But again, you know, in published papers and won sort of prizes and stuff, it will look good. And then finally, in the 1950s and 60s, we invented atomic clocks. And you could rent a seat on a jumbo jet and put a bunch of atomic clocks next to you, fly up 10 kilometers above the Earth and land, and show that that clock had ticked faster than the one on it. And so this was done in, I think, the 50s and 60s and shown to be correct. But in terms of gravitational wave detection, Einstein thought this would be impossible. So what happens when a gravitational wave is generated? Space and time get squished and stretched. And when they're getting squished in one way, they're getting stretched in the other. And so they go through the universe like this, stretching and squeezing things. But the effect is so incredibly tiny that Einstein thought this would be completely impossible. So why did he think that? Well, the densest objects he knew about when he was alive were things like planets and stars. So if we look at how big the Earth is compared to the Sun, we can actually stick the Earth above the rings of Saturn. And you can see how big the Earth is compared to the giant planets. And then the Sun is just sort of like gigantic, but the Sun is not very dense. So if you want to generate gravitational waves, and you're Einstein and it's 1950, and the densest objects we know about in the universe are stars like the Sun and even white dwarfs, which we'll get onto in a minute. It's impossible to believe that you'd ever be able to detect gravitational waves. So he thought this was a bit of a fantasy. And in fact, he even doubted his own work so much that he tried to retract the paper that predicted gravitational waves. And they went to a referee, and the referee said, "No, Einstein, you're actually right. There are gravitational waves." And he was so offended, he never published in that journal again. So he tried to retract his own correct work. If we look at the universe, there's this, our sun might be 1 solar mass, but there's other stars that are 20 solar masses. And these are gigantic compared to the sun. And the only reason they look comparable is because of a clever camera angle. But if I was to zoom out, you would see how big our sun is compared to Rigel. It's a tiny little pathetic star, but it's a very nice place to live if you like a stable climate and you need millions of years to evolve into humans. So this is the star Rigel, and this is a life-size depiction of how big it is compared to the sun. And we can learn a little bit about this star. It's about 20 times heavier than the sun, but it's 80 times the radius. It has a temperature of 21,000 Kelvin instead of our sun, which is about 5,500. Its luminosity is 100,000 times worse than the sun. So it's giving off 100,000 times as much energy, but it only has 20 times as much mass. So it doesn't live for very long. So a star like the sun will live for about 10,000 million years, but Rigel is only going to live for about 10 million years. So luckily for us, these stars burn all their fuel. They convert hydrogen into helium and helium into carbon. They get up to iron. And then the center of the star gets so big that it can't withstand its own gravity. And the poor electrons and protons are combined together to neutrons. There's no longer any electrostatic repulsion keeping the core from collapsing. It collapses down and blows up and leaves behind a supernova, which is a very bright star in the sky. And at the core of the supernova is either a neutron star or a black hole. So on the left, we have the Crab supernova remnant. This is a star that blew up in 1054 AD. And it was actually witnessed by the Chinese astronomers. At the right is what's called a planetary nebula. And the planetary nebulae leave behind what's called a white dwarf. A white dwarf is about the size of the Earth, but it's about 500,000 times heavier. Oh, sorry, 300,000 times. No, not even that. About 200,000 times heavier. About 0.6 of a solar mass. At the center of this supernova remnant that leaves behind a neutron star, we have a pulsar. Yay! My favorite objects. And neutron stars are far more dense. So to get an idea of what our galaxy looks like, we can look at our nearest neighbors. This is the Andromeda galaxy, visible from Canada, not very visible from Australia. And we think that the Milky Way looks a little bit like this. There's a disk of stars. The blue ones are very hot and young. In the core here, there's a lot of boring old stars. And we think we live in a galaxy like this about 2/3 of the way out. So if we want to look at what our own galaxy structure is like, we have the central bulge, and we have a bar, and then we have these spiral arms, and we live about 2/3 of the way out. But our galaxy disk of stars is actually very, very thin. So as it will wash by us, this is about the height of where the young stars are born in our galaxy. The older ones are sort of puffed out a bit. But this is a bit like our galaxy. And we're trying to study neutron stars which are born in this disk. Some galaxies are really boring. They don't spin enough to actually form a disk, and so they only have one wave of star formation and then just a lot of boring dead stars. These are our nearest neighbor galaxies, the Magellanic Clouds. These are visible from Australia. If you come down, you can actually see these with your eyes. And Magellan was the first European navigator to kind of catalog them. This object here is something called a globular cluster. That's about 1 million stars in a little spherical blob. And all sorts of fun things happen at 4 of them. How am I doing for time, Mrs. Chairman? All right, so galaxies are represented by these dots, and they're actually form these clusters. And when we look out into the universe, we can see stars and galaxies that recede or are billions of years away. If we use a radio telescope, we get a very different view of the sky. This is made with the Meerkat radio telescope. And this is the center of our galaxy. And at the center of our galaxy, there's a supermassive black hole, which is giving rise to a lot of this burning material. And these objects here are actually supernova events. These are stars that have blown up. And my favorite thing on this diagram is right here. That's actually a supermassive black hole, millions of light years behind our Milky Way galaxy, spewing out jets of material. So I use this telescope, and I think I met Vicky at this telescope maybe for the first time. We used to observe together in the control room. And the Parkes telescope was instrumental in discovering the first quasar. This is a jet of material being spewed out that you can see in the radio. And the idea is that there's a supermassive black hole with an accretion disk squirting out these jets. Our favorite astronomer is one called Jocelyn Bell, and she used this rather boring-looking radio telescope to discover a new type of star. For her PhD, she used to freeze at night, making observations of quasars as they were doing what's called scintillating in the interplanetary medium. And she was very perceptive, and she noticed that every now and then there was a scruff of a chart recorder. We actually used to make measurements by having ink in pens, and paper used to pass underneath the pen. And if ever there was a signal, the pen would go up and then go back down, and you would get the paper and you would have to analyze it. And she was clever enough to realize that this, what she called a bit of scruff, was repeating and was happening 4 minutes earlier every day, which is what happens when something's going around or is embedded in the sky and not embedded in the earth. And she could somehow tell the difference between that and the interference, which looks remarkably similar. Anyway, when she sped up her chart recorder and used the whole year's budget of paper, she discovered that every 1.3 seconds there was actually a burst of radio emission. And we now have this model of the neutron star or pulsar, so discovered by Jocelyn. The idea is that there's an object rotates. This one's rotating every 2 or 3 seconds. And if the beam is pointing at us, we get a flash of radio waves. And this is what we believe that she had discovered. We now know that these things weigh about 500,000 Earth masses and are only about 20 kilometers in radius. There's about 3,500 known, and about half of them have just been discovered at the Parkes telescope. So we've already seen what gives rise to them. If you show how big they are, at the end of a star's life, it either becomes a neutron star. If it's really big, it becomes a black hole. But most of the stars in our galaxy become something boring called a white dwarf, which is considerably bigger than a neutron star and won't be talked about too much more in this talk. So we can use the finite speed of light in the universe to work out how far away a neutron star is. And if we do that, it kind of disappeared. Let me just zoom out a little bit. Oh, this is where all the neutron stars we know of are in our universe. So we believe there's probably billions of neutron stars, but we don't really see the ones in the nearest galaxies. And so they're a galactic population, which is disk-like. If you squint, you can kind of see spiral arms in there. And there's a massive what we call selection effect, in that it's easy to discover nearby pulsars because they appear brighter. The ones on the other side of the galaxy are just too faint for us to see on the whole. And then if you're really good, you can see that there's a couple of clumps of neutron stars. If I'm really good, I'm going to find them. Where are they? Let's zoom out a bit. No, we've zoomed out. We're on max zoom. This is not good. You can see the galaxies in the Magellanic Clouds. I think in the interest of time, I might have to do that after questions. All right. Oh, there they are, back here. That's the Large Magellanic Cloud and the small. So people used to discover these things by looking at pen chart recorders. We don't do that anymore. We use computers. And in the 1970s, Vicky's old supervisor was the first person to do a computer search for pulsars, and he discovered this amazing thing called the binary pulsar. And the binary pulsar was not only unique, it was the first one to be going around another star. It went around its other star not like once a year or something. It went around every 7 3/4 hours. And instead of the perihelion advancing by 43 seconds of arc a century, it advanced by 4.2 degrees a year. And that enabled him to measure how much this thing weighed, and it was 2.8 times the mass of our sun. And he realized that in 20 years, he could win the Nobel Prize if he proved that this thing emitted gravitational waves, because the orbit should shrink by 3 millimeters in orbit. So even though the orbit was something like 2 million kilometers across, if you could just measure it, that it was shrinking by 3 millimeters in orbit, Stockholm weighted. So the reason this was possible is that if you shrink by 3 millimeters in your first orbit, you actually shrink by kind of 6 millimeters in the next orbit, and then 9, and then 12 millimeters, and we're still only talking this big. And this thing is like about 10,000 light years away. So how do you do it? Well, it gets back to the point of closest approach later and later, or sorry, earlier and earlier, because the orbit keeps shrinking and shrinking. And in fact, after like 10 years, it was actually arriving back at the point of closest approach about a few seconds earlier. And with very careful measurements, he actually showed that's correct. So when we look at pulsars, this is how rapidly they spin, and this is their magnetic field strength. These are what's called common or garden pulsars. They rotate about once a second and have these very high magnetic fields. The Nobel Prize winning pulsar is down here in the middle. It actually rotates every 59 milliseconds. But some pulsars rotate almost 1,000 times a second. And in fact, Jason Hissels, who's coming here as faculty, is the world record holder. And I think he has a 700 hertz, 716 hertz pulsar. So it rotates 716 times a second. So how does that happen? Well, binary stars start off with a big star that wants to live fast and die young, and a kind of a good star like the sun that sort of says you've got to quit smoking But after only just a few million years, this star swells up to become a red giant. It dumps material on the companion, and it now becomes the big star. And it says, I can see what you're smoking. That's good. So this star here is almost ready to die because it's used up all of its hydrogen, and it blows up, and we actually end up with a neutron star going around the main sequence star. And in fact, Vicky Caspi discovered one of the first, actually, she didn't discover the pulsar, but she discovered that it was a binary with Matthew Bales's help in the Parkes control. And there's a system that takes about 52 days to go around, and it has a highly eccentric orbit called 0045-7319. And so we discovered this pulsar a long time ago, and we showed that the orbit was actually changing its orientation because the neutron star had been kicked by a powerful explosion upon birth. After the good star eventually ends its life, it swells up and it transfers matter onto the neutron star. And the energy density when the material is falling onto this hypercompact object is actually equivalent to 100,000 nuclear wars per meter squared per second. And yet it doesn't damage it too much. But what it does do is it makes the neutron star spin faster and faster. And you end up with what's called a spun up neutron star and a pre-supernova star. And sometimes this thing just peters out and becomes a white dwarf, and it's really boring. But sometimes it blows up. And when it does blow up, you can get another neutron star. This is a boring one. Let's move on. This is the more exciting case when you have two neutron stars going around each other. They have these highly eccentric orbits, and they exhibit all sorts of relativistic effects that enable you to get to Stockholm and win Nobel Prizes. The prediction was that because that system existed, it should keep shrinking by millimeters and millimeters, and after about 300 million years, the two neutron stars would be going around each other, not every hour or a few hours, but every 1 millisecond. And at that rate, the gravitational wave emission should be so strong, they would rip each other apart, and you should end up with a black hole. And the whole universe should shake at about 1,000 cycles per second. And if you went to Congress and you said, I need $500 million to build 2 vacuum tubes at 90 degrees apart, and I fired the world's most powerful laser down this vacuum tube and the light bounced back, I would be able to tell the difference between the distance to the mirrors if a neutron star merger happened anywhere within about 120 million light years. And so they gave them the money. We'll see how that works in a second. So this is our binary pulsar discovered by Joe Taylor and Russell Holz. They knew the masses, they knew how much it should be shrinking, and they predicted that gravitational waves should be emitted and that the orbit should shrink. And this is how much earlier you should arrive at what's called periastron if gravitational waves existed, compared to if they don't. If they did exist, all the data points should lie along this line. And look, this is normal astronomy. Normally everything's out by a factor of 2. These were the arrival times, and it was like bang on. And so about here, about 1993, Joe Taylor won the Nobel Prize for physics with Russell Holz. And then he stopped observing and he became a dean. Don't do that. So the advanced LIGO detector was built, and it really does exist. It's 4 kilometers long armed. There is a powerful laser beam. The light travels down for 4 kilometers, bounces off a mirror and comes back. And it's tuned so it's exactly 1/2 a wavelength different than the other arm. And so the light cancels out. You don't get any light. So if a gravitational wave goes by, you jiggle and you should see light. And so on the 17th of August, 2017, actually, before that I visited because I was on some committee, but they turned on the detector and this remarkable thing happened. They actually saw a gravitational wave pass through the detector and cause the mirrors to shake at an increasingly high rate as the neutron stars went faster and faster around each other. And then 1.5 seconds later, a burst of gamma rays hit the Earth. And they discovered gravitational waves, and they knew that it must come from some part of the sky. So they grabbed every telescope on Earth, And they saw that there was a brand new star, and this is actually the result of two neutron stars emerging and proving that gravitational waves actually do exist. And everybody looked at this thing for a week or so, and then it faded out. But this is actually how gold is made in the universe. When neutron stars are ripped apart, you make gold. So if you have a wedding ring, doesn't mean I'm single. Then it's actually because neutron stars somewhere merged and sprinkled material throughout our galaxy, and we ended up seeing it. So I might quit there because I think I'm out of time. But if anybody has any questions, I'd be happy to take them. Especially one of those questions is, what are you going to show us next?
Any questions? Yes. Video on YouTube.
Sorry.
I saw a video on YouTube.
Uh-huh.
I think it's true. But it was it's like an apple in a box, and it says that the time, like it's an experiment, and the time sample would eventually decay and disappear, and would eventually come back together, and like be another apple, which I was wondering if it could be the same apple or considered another apple.
I'm not sure it's true, but I think the apple would decay, but I wouldn't magically reform an apple.
But I think it was like in there.
I think it was maybe
Like,
saying that,
they took it as a magic out of the box. So
okay, maybe an astrophysicist isn't the right person to ask. But they might have been trying to explain that material from the apple would go into the atmosphere or whatever and be recycled and not form another apple. I'm not sure what the point was. Sorry, I don't know much about apples.
So a lot of the objects right now you're measuring neutron stars, black holes, very big and violent, right? So I mean, maybe can you give us an idea of like, what the limit to this is? Obviously, I guess.
Yeah, so LIGO has gone on to do great things. So I think they're now up to about 200 mergers that they've seen. That one I showed you was about the 8th or 9th. The first one they saw was actually from two 30 solar mass black holes coalescing. Unfortunately, the frequency of the gravitational wave depends on the masses of the things you're looking at. And the heavier the object, the higher amplitude the gravitational wave is, but it's a slower gravitational wave. It's got a lower frequency. And the detectors are not very good at detecting anything that's bigger than about 1,000 solar masses. So our current generation of gravitational wave detectors would struggle to see 2,000 solar mass black holes because they just take too long to go around each other. The neutron stars go around each other about 1,000 times a second. They're a kilohertz gravitational wave. And that's actually getting too high a frequency for LIGO. LIGO loves things around 100 hertz. So as you get a bigger and bigger black hole, they might exist and they might be out there and they might be merging, but LIGO can't tell us so much about them. Your kind of typical coalescence that you see with LIGO is around about a 20 solar mass black hole coalescing with another one. I think their lightest, they've had two neutron stars merge, but one of them there was only one detector on, so they couldn't work out where it was in the sky. And there's been a few black holes with neutron stars merge. I think there's a couple of them. But if it gets too big, the frequency of the gravitational wave is just so slow, you can't tell the difference between that and just what's called Newtonian noise, where somebody walks past your mirror, the gravity kind of affects it and stuff. It's actually really hard to do low frequency gravitational waves, but there is a future mission called LISA that'll be quite good at that, and that's going to be laser beams fired in space in an equilateral triangle trailing behind the Earth, which will be remarkable in about 2034.
For building, what kind of arms, what kind of
Yeah, so we actually knew very little about binary black holes before LIGO, because binary black holes don't give off any light. And so they were more of a theoretical postulate. Like, we knew there were big black holes. We weren't sure that they were ever close enough to merge in what's called a Hubble time. So the whole system was really optimized to discover neutron star mergers. And while they were testing it, they hadn't even started their official observing run. They were testing it. And this incredibly high signal to noise event happened where 230 solar mass black holes completed about sort of 5 orbits of each other. And they saw it in both. There was a detector in Livingston, which is in Louisiana, and also in Hanford in Washington State. And they saw exactly the same thing, separated by about 7 milliseconds, which is about the light travel time between those two detectors. So what they do is they look at the frequency of the gravitational wave and they use that to infer what the masses of the systems were. But it's probably fair to say that they were shocked at how many black holes, or how much easier the black holes were to discover than the neutron stars. Unfortunately, when the black holes merge, they don't leave anything behind except a bigger black hole. And so you can turn every telescope in the universe at it and you can't see anything. Whereas the neutron stars, when they merge, they kind of light up the sky and it's all very exciting. And there's bursts of gamma rays and all sorts of happy experiments you can do. Whereas we're so laissez-faire now. Whenever LIGO says, "Yeah, we found two mergers this week," you go, "Yeah."
Other questions? And I do want to encourage our younger audience members to ask questions if you have them. So, any others? How FRBs are related to Einstein's theory.
Yeah, well, the first FRB was discovered maybe 17 years ago, and we didn't know what it was. In fact, we didn't know it was real, but it looked incredibly real. And we knew that it didn't last very long, so it only lasted about 5 milliseconds. So we thought whatever caused it was probably smaller than 5 milliseconds times the speed of light. And then we just started discovering other fast radio bursts, and some of them were even more or short time scale. So we kind of know that the emission region can't be much more than 100 kilometers. And if you look at a white dwarf, they're more like thousands of kilometers. So we believe that they're probably coming from neutron stars. Lo and behold, CHIME, famous CHIME telescope, managed to see a fast radio burst from our own galaxy. It was kind of puny in terms of its luminosity, but it was incredibly important in that it happened at the same time as an X-ray flare from a known magnetar, which is a very magnetic neutron star. So we know at least one fast radio burst out of like 5,000 has come from a neutron star, and all the rest of them are conjectured. Like, they're all based on theories. But my personal belief is that probably almost all of them come from magnetars, but there could be a set of other objects that have magnetic fields and the right circumstances to also have explosions that give rise to fast radio bursts.
I have a question on the clusters, just because I remember you pointed them out, and there were like 100 million stars in there. What exactly?
1 million.
Oh, okay. But what, like, how do they not, or maybe they do over time, get closer together, or is it because they're such all massive stars that kind of stabilizes?
That's the best question ever, because I happen to have some slides on them, which would have been near the end of my talk. But let's face it, I had enough to occupy 2 hours or something. Yeah, no, I'm embarrassed too. But globular cluster. So this is what a globular cluster looks like if you're fortunate enough to get Hubble Space Telescope time. So they are actually concentrated at the core. And what actually happens is the binaries in these systems interact with other stars, and they eject usually the lighter star, and the binary becomes what we call hardened. So they go around each other faster. And in the cores of these things, occasionally there gets a runaway process where that happens more and more often, and you get what's called a core collapsed globular cluster, where you end up with so many interactions that at the end puffs up again. And this is a core collapse cluster that this telescope Meerkat has been pointing at and discovering pulsars in. And one of them just happens to be NGC 1851e. So it's a neutron star going around another star, and it has this highly eccentric orbit. It means when you plot the period versus time, it changes in this very systematic way. And unlike pulsars that get recycled and have their star peter out and become a white dwarf, this one has an eccentric orbit. And so my friends and I have been observing this system, and we think that rather than a circular orbit, that is what happens after you've recycled your neutron star, you can actually have a third body come along. And this is where the Jaws music starts playing. So you can have a peace-loving circular orbit system where the white dwarf progenitor spun up the neutron star, and then the black hole comes in and it tries to disrupt them. And they go into this little dance, which I can make look even better by where temporarily the black hole and the white dwarf are gravitationally bound, and the neutron star is trying to get away, but it doesn't quite have enough energy. And then it gets pulled back towards the black hole and white dwarf. And then we can see what happens. They do this triple body encounter, and bammo, the poor old white dwarf gets ejected. And you end up with an eccentric system that we can see. So it was a very perceptive question, and I got to show off my fancy thing. So thank you very much.
We have time for one more question.
Just following up on the image you just showed us, the fact that they're like their mass are all, they're all never getting in contact with each other because they're bending each other's masses.
So Newton says that objects like to travel in straight lines, whereas objects experiencing an external force. And it's actually really hard to get things to meet head on. But what will happen in these systems is they give off gravitational waves, and that makes them sort of spiral together, and eventually they rip each other apart. And so it's thought that maybe some of these black hole neutron stars that we see with LIGO are actually the cause of globules. But it may be that they've just formed on their own. It's a little bit of it's an interesting area of research.
Quick question, okay.
Do amateur astronomers contribute to this research at all?
So there's not many amateur radio astronomers, and most of what I've showed is because of radio. Gravitational wave things are even worse. Like you can't just build your own gravitational wave detector. It costs about $1 billion. But amateur astronomers do monitor the sky for what's called variable stars. And until about the mid-90s, amateur astronomers were incredibly important for discovering exploding stars called supernovae. And there were lots of people that every night would just look at the same galaxies over and over, and they had them memorized in their head. And they actually used to dominate the sort of supernova discovery rate. Sadly, these days there's these automated things that go around, but they still contribute to those researches.
Join me again in thanking Professor Bales. Have a great night. Thank you.
And about 5 times Okay. It's very easy to monitor how much heat the sun is giving off.